Hi everyone, we're going to continue with chapter 8, looking in more detail at some reactions of alkenes, in particular more addition reactions. So the first addition reaction we are going to go into today is the hydroboration oxidation. So it's a two-step reaction, hydroboration followed by oxidation. So we talked about addition of an H and an OH group over a double bond, which forms an alcohol, and how this happens through hydration, right? We take a water molecule and we're going to add the proton and then the OH separately. And this happens normally in a Markovnikov fashion, meaning that the OH will add to the most substituted position. However, what if we want the OH to end up on the least substituted of the positions along that double bond? Well, we can do this. We can add on an H and an OH in an anti-Markovnikov fashion, so against the Markovnikov fashion, using a special type of reaction. Normally, in our reactions, hydrogen is electrophilic, but to achieve a non or anti-Markovnikov reaction, we have to have hydration using a nucleophilic source of hydrogen. And that is going to come from our HBr2, our boron hydride. You can see it here. This is boron connected to any type of carbon groups. That's what the R stands for. Remember, R is on an element. It just means that there are carbons there. And it has a hydrogen on it. This hydrogen is a nucleophilic hydrogen and not an electrophilic hydrogen. Most of our hydrogens, including in a normal hydration reaction, have some positive charge on them. And the mechanism of this reaction, this hydrogen is actually slightly negative in its charge, so it is nucleophilic. So during a anti-Markovnikov hydration, during this hydroboration reaction, we add on the Br2 group separate from the hydrogen group, and they add on where the hydrogen adds in a fashion that is connected to the most substituted group, and the Br adds on to the least substituted group. Once this step is finalized, we're going to convert that Br2 group to an OH group. So after the Br2 group is added, and it gets added again onto the less substituted side, then we add hydrogen peroxide to form an alcohol where the Br2 group once was. So this is called an oxidation step, and it converts our Br2 to an OH. Ultimately, this again leaves us with an alcohol where the OH is on the least substituted group and the H is on the most substituted group. Here's another example of that in full. Just again showing that you take a double bond and it's a two-step reaction. The first is adding boron hydride to form your H and Br2, your organoborane, and then an oxidation with hydrogen peroxide to form the final alcohol of interest. Borons that you can use include B2H6 and any addex of BH3 with a Lewis base. So these can be things like BH3THF, BH3 O. This is an O with an ethyl group on it. 2 ethyl groups. That's the ET2. Generally, any of these will work as your borane group. Again, this is a 2-step process. We have to do the first reaction with your boron group, followed by the oxidation group reaction with your hydrogen peroxide. However, they are typically written together. And again, they always result in the OH ultimately being in the less substituted position. Hydroboration is also a syn reaction. So even though, again, it's a 2-step, the hydroboration followed by the oxidation, which retains that conformation, is syn, meaning that overall, when you do this hydroboration, you have the hydrogen and the OH on the same side of each other. Here you can see a methyl cyclopentane. Here's our double bond, and we're going to open that double bond up. Now, notice the OH goes on the less substituted position here, in this case, and our hydrogen is not shown, but it's down here. Notice it is also down because the OH and the hydrogen that were added are syn. They get added on the same side and away from where the methyl group was. So if you were to do a hydroboration oxidation of one of these, which would yield a primary alcohol as a major product? Now remember, hydroboration oxidation is going to put the OH group on the least substituted position in this case. So let's just think about opening up these double bonds. I'm just going to draw where that OH would end up if we were to do a hydroboration. So here, this double bond would break, adding an OH here on the less substituted side and a hydrogen here. For B, this would break. Now notice these positions are actually equal. So it doesn't matter where I write these, they have an equivalent substitution. For C, again, this side and this side are generally equivalent. You have a bulkier group here, meaning generally you're going to push your first group to the other position. But again, they're equivalent in their positioning, in that this is a secondary, this would form a secondary carbocation, and this would also form a secondary carbocation. Here we would ultimately end up with our OH here and our hydrogen here. Again, on this one, OH and hydrogen. Again, OH is ending up on the less substituted, in this case for a hydroboration oxidation. So looking at our final products, which one of these is a primary alcohol? That would be A, an OH group that is attached to a carbon with only one other carbon attachment. Okay, another reaction of alkenes is called an epoxidation reaction. To understand epoxidation, let's first talk about epoxides. Epoxides are a three-membered cyclic ether. They're a three-membered ring made up of a carbon, and an oxygen in a ring. This is also called an ether because ether groups, if you remember, are oxygens sandwiched between carbons. And technically, this oxygen is sandwiched between two carbons. The way that you can name epoxides, they can be named in two different ways. One is via the numbering position. They are along a chain, where this would be the first position number, and then n+1 is the second position number. It then gets the word epoxy, and then the rest of the name of the group. So this epoxide would be a side group along a chain. And again, you're going to number where its carbons are along a main alkane, and it fits in just like any other side group along with a name. So here in our first one, this ring we know is a cyclohexane, and we can say that the epoxide group is on carbons 1 and 2. So its whole side group name is 1,2-epoxy cyclohexane. Here is another example of a chain. So our longest chain is actually 4 long. It would be here, 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 and here, making it a butane. Now notice that epoxy is on carbons 2 and 3, so it gets a name of 2,3-epoxy. And there is also this extra methyl group, which is where the 2-methyl comes from. It's on the 2 position. This is the main way that you name epoxies. You can also name them by saying the alkene that they would be making with the word oxide following. So for example, ethylene oxide. Again, this is a common name, and the naming format we're not going to be using. Instead, use this format in which you're numbering the epoxy group as if it was just another side group along the carbons where it is, and then putting it in front of the alkane name. Now, an epoxidation reaction is the addition of a single oxygen atom across an alkene, ultimately forming an epoxide. So you're taking a double bond and you're making an epoxide. You're adding that oxygen where that double bond was. To make an epoxide, we need something like a peracid or a peroxy acid to form an epoxide. You'll normally see peroxy acid. Notice it has this interesting 2 oxygens bound together. This actually looks, if we draw this out, like this. This is a special type of group. So this 2 oxygens bound together. This is important for the formation of the epoxide, which is why we need to use a peroxy acid for epoxide formation. And note that the corresponding byproduct is a carboxylic acid. Remember, carboxylic acids, if you look at your functional groups, are carbonyls. So they have this double bond to oxygen that have an OH group on them. This is the general format of a carboxylic acid. So you form an epoxide from your double bond, and you're left with a carboxylic acid. So here in our example below, you can see we take cyclooctene. This is a 8-membered ring with a double bond, and when it's reacted with a peroxyacetic acid, this is some type of peroxy acid, it forms an epoxide where the double bond was. And notice that our peroxyacetic acid just becomes acetic acid, which is the carboxylic acid form of what's left over from our starting peroxy acid. For epoxidation, the same trends that we've been seeing hold true in that more substituted alkenes react more rapidly. So the alkene acts as a Lewis base, and this is true for also our addition reactions that we've been looking. That means that the per acid or peroxy acid naturally, as you might guess, acts as a Lewis acid in this reaction. The addition of the oxygen is also a syn reaction, and groups that were cis in the alkene in the original double bond will remain cis in the epoxide. So if you started with a double bond like this, you would end with an epoxide like this. So your groups would still be on the same side. This syn reaction and the syn addition actually comes from the mechanism of action in epoxidation. It's a very intriguing way that oxygen is delivered. The oxygen that is delivered is actually this oxygen attached to the hydrogen on the peroxy acid. What happens is this double bond is going to donate electrons to grab this oxygen, which then breaks off of our main acid, forming a double bond here. This double bond then opens up and takes the hydrogen that was being detached and forms our acid. So you can see you actually have a full rearrangement of the original peroxy acid, in which where the double bond was is now where the OH was, and where this oxygen was is now where the double bond is on the acid. An interesting reaction. You don't need to understand or memorize this particular mechanism, but understand that because of the manner of this mechanism in this concerted action, you do have a syn addition of the epoxide. Another reaction of alkenes is called ozonolysis. This reaction uses ozone as a substrate. Remember ozone? Here it is shown. It has two resonance structures that exist equally, and it can be both an electrophile and a nucleophile because it has a positively charged oxygen and a negatively charged oxygen on the same molecule. Ozone can react with an alkene to form this complex molecule called an ozonide. This formation is very favorable. You can see it acts almost like an addition reaction in which we're adding a OO group and an O group. These are the two separate pieces, right? The electrophile and the nucleophile that are being added across this double bond. Now, ozonolysis is actually used more often in a combination with a subsequent reductive step. This uses this sulfide group to open the ring and form two carbonyl groups. So instead of forming this ozonide group, what happens is essentially we split this double bond in half and form a carbonyl on each of those halves. Synthesizing carbonyl compounds in general from something that has all carbons can be difficult, which is why ozonolysis is a great reaction for adding in carbonyls or adding in oxygens when we are doing a multi-step synthesis. Again, it essentially splits the alkene down the middle, if you think of it that way, And now there is a carbonyl on each of those halves. So for example, this splits here and we get acetone. Here's our one carbonyl that's formed, and 2,2-dimethylpropanol, this aldehyde that is formed. Let's do a test question. If we were to do an ozonolysis, an ozonolysis of 2,4-dimethyl-2-pentene, what would it produce? So remember, when we're saying an ozonolysis, generally we're talking about the addition of ozone plus the reductive step. So it is a two-step reaction that generally we talk about as one reaction together, an ozonolysis. Okay, so let's first draw out our starting reactant and see what it would produce. We have a pentene. So it's 5-membered chain, 1, 2, 3, 4, 5. It has a double bond at position 2. That would be here. And 2,4-dimethyl. So 2 methyl groups on position 2 and 4. So here's position 2, and here's position 4. Now, if we were to do an ozonolysis, we would break this double bond in half, and each of those halves would then have a carbonyl in the end. So for example, this half would look like this, and our other half have a double bond here. And what's not shown here, just to make this clear, is there is a hydrogen. You can leave it as a blank spot, but if it helps you, draw that hydrogen out. So these would be our products after splitting this in half, which you can see is answer B. Now let's talk a little bit about retrosynthesis. You're going to be seeing retrosynthesis more and more as you delve further into organic. And now is a good time, now that we've kind of talked about multiple reactions, to bring up the topic. Retrosynthesis in general is a way to do multiple steps using reactions we've talked about to get from a starting material and generate a target. Alkenes in particular, double bonds, are really useful in their synthetic waypoints for other functional group transformations. So for example, if we wanted to make 1,2-epoxy cyclohexane, this is our target, we want to make an epoxy, and we're starting with an alcohol. Currently, there is no reaction that converts alcohols to epoxies directly. We want to think backwards of how we can make an epoxy group if we're starting with an alcohol. So one thing we just talked about, for example, is that we know that an epoxy group can be generated from a double bond. And we also know from previous reactions that we can dehydrate an alcohol to make a double bond. This is how you would do retrosynthesis. We'd go backwards thinking about what our product is and go back step by step until we get to a reaction with our viable starting material. So as shown below, again, we know that a 1,2-epoxy cyclohexane can be made from cyclohexene, which can be made from cyclohexanol. And if we were to write this now in the forward direction, this is starting with the alcohol and showing our final product, the epoxide that we want, we can now add in all of the information. So we know if we start with cyclohexanol, We can do an acid catalyzed elimination using heat to form a double bond, and then use a peroxy acid to then form our epoxide. Okay, so that is it for the general topics of Chapter 8. Again, review all of the different addition reactions that we've gone over, other reactions of the double bond, including epoxidation and our ozonolysis. And lastly, I brought up the topic of retrosynthesis, but think about combining these reactions and how we can go from a starting material to a final product. So I will be incorporating some of the reactions we've seen before, like eliminations or substitution reactions, along with our addition reactions of alkenes, etc.